Hi, everybody, and welcome back. So today we're going to talk about projectile motion. Now, we saw some demonstrations already about projectiles, and what we found most importantly is that a projectile can move in both the horizontal or the X direction and also the Y or the vertical direction at the same time. And the demonstration that we saw when we had a conversation about, a bullet fired versus a bullet dropped, and we did the demonstrations, is that those two motions are completely independent of each other. So we need to make sure that we understand what that means. They have no effect on each other at all. So they're totally independent or separate from each other. So what's happening in the X direction and what's happening in the Y direction, totally independent. They don't affect each other in any way. But this form of two-dimensional motion, X and Y motion that we have, is called projectile motion. And just to be clear about what is a projectile, basically any object that's in free fall. And we talked about free fall before. We learned that if an object is flying through the air and it's under the influence of only gravity, then it's in free fall. And that makes it a projectile. So if we kick a soccer ball, like once it's kicked and it's off the ground, it's a projectile. If it's rolling along the ground, not a projectile because there's friction acting on it. All right, if we take a baseball and we throw it through the air, that's going to be a projectile. Okay, if we fire a bullet, that's going to be a projectile. A rocket would not be a projectile because it has an engine that propels it, or an airplane would not be a projectile. All right, so it's got to be moving through the air, and gravity being the force that is the only force that's acting on it. That makes it a projectile. Okay, so in order for us to understand projectile motion a little bit better, there's a couple assumptions that we need to make. And the first one is that the acceleration is constant over the range of motion and directed downwards. We use the symbol g because we're talking about the acceleration due to gravity. Gravity is going to be pulling down on that object the entire time it flies through the air. And it's going to be pulling in a downwards direction with an amount of 9.8 meters per second squared. We learned about free fall before, so this shouldn't be anything new. Gravity's pulling down on this object and causes an acceleration in that direction, in downward direction of 9.8. All right, the other thing that we're going to assume is that the effect of air friction or air resistance is negligible. So once we throw that object into the air, yeah, maybe the air is pushing against it a little bit, but we're going to neglect that effect. The effect that air has on most projectiles is very small, and so we can pretty much ignore it without having to have any, major consequences of ignoring it. For some objects, air resistance might be a little bit more significant, but we're not going to worry about that just yet. So if we follow these two assumptions, that the acceleration is constant downwards and that there's no air resistance, then the object in projectile motion will follow a parabolic path. Parabolic path means that it makes the shape of a parabola in the air. So when we throw an object up in the air and it flies through the air, the shape that it's going to make is going to go up and down like the shape of a parabola like this. And every single projectile is going to follow some sort of shape like that. Now, those shapes might be a little bit taller and narrower, or they might be wider and not as tall. Depends on how we launch it. But the path that it takes overall is called a trajectory. So whichever path that particular projectile takes is called a trajectory. Every single projectile is going to make some sort of parabola shape, but some of them, different in terms of how tall or how wide. Okay, so it's helpful to understand this by taking a look at this diagram. All right, so here we have a cannon, and this cannon is being fired at an angle on like the ground, on flat ground. And the green line here represents the path that the cannonball would actually take as it flies through the air. So we can see it makes the shape of a parabola, and it would fly through the air and then land on the ground. over here. Now, the dotted line, that represents the path that the cannon was originally aimed at. So if you can imagine if the cannon had like a laser sight on it, this is the direction that that laser sight would be pointed. All right, in this direction. And if there were no gravity, this is the path that that cannonball would take. But we know that it doesn't because gravity's pulling down on it the whole time. All right, so what we need to understand is what's going on with this projectile horizontally and what's going on with this projectile vertically. So when we look at it from a horizontal standpoint, once it's launched into the air, its motion doesn't change in a horizontal sense. It's constant velocity. And the reason for that is because once it's flying through the air, there's nothing propelling it forward anymore. Like, yeah, it was launched, but it's not being pushed anymore horizontally. And if we're neglecting air resistance, then there's nothing pushing against it either while it flies through the air. All right, so if there's nothing propelling it forward to go faster, and there's nothing pushing against it to go slower, then it's going to move at whatever speed it was launched at. So horizontally, the motion never changes once it's launched. So in my picture here, we see I marked out some spots on the ground over here. You can imagine if we fired this cannonball, maybe the object would travel 10 meters downrange in the first second, and 10 meters the next second, and 10 meters the next second. Whatever it is, it's going to be the same amount of distance every second because it doesn't speed up or slow down horizontally. Why not? Because there's no force on it horizontally. Okay. But vertically, totally different story. Vertically, we have free fall. This object's under the influence of gravity, which means it's going to have a constant acceleration downwards. And so the distance it travels vertically doesn't stay the same. The amount that it falls from this dotted line gets bigger and bigger because it's accelerating downwards as it moves through the air. And it accelerates downwards because of gravity. But again, to repeat for emphasis, this motion, the horizontal motion, and this motion, the vertical motion, they don't impact each other in any way at all. This is separate from this, and they don't interchange. So in the demonstration we did, we saw that if you took an object and dropped it straight down, and you took another object and you launched it sideways, not at an angle, up or down or anything, but just straight out like this, then they both end up hitting the ground at the same time. Now, this is a picture of kind of what it would look like if we took a picture of where the object was at different points in its flight path. So you'll notice this green one that's thrown sideways, as it flies through the air, it's falling. It's falling, falls some more, falls even more because of gravity. Gravity's accelerating it downwards. This one that's dropped is also falling and gets faster and faster. But what we notice is that both of these, if they're launched at the same time, they're both always at the same height because they're both falling at the same rate. They're both falling at the same rate because gravity's acting on both of them, giving them a constant acceleration. The fact that this one is moving sideways doesn't change the fact that it's falling downwards. It still falls downwards the same way. The only difference is, while it falls, it also happens to move sideways and cover some ground as it goes. So we see it take this parabolic shape of its path. So if we look at an object, let's say it was launched from the ground and it's launched at an angle, you can see this bold red vector here for the initial velocity. So let's say it was launched like this. We can imagine that that motion is actually two pieces, a horizontal part or a component and a vertical component like this. Now here's what I want you to pay close attention to. Notice that the horizontal component of the motion is always the same. If you look at the length of these horizontal vectors, they're all the same length because the object is going the same speed horizontally every second as it moves. Nothing to slow it down, nothing to speed it up. All right. But vertically, it does change. Look how long the vector is at the beginning. It gets shorter here. It's actually 0 here. Now it becomes negative, and now it becomes even more negative. Think about why. Here it is, gravity. Gravity is acting on this vertical motion. It slows it to 0 as it travels up, and then as it comes back down, it gets faster and faster in a downwards direction. All right, so the horizontal velocity remains the same throughout the entire motion, while the vertical velocity is decreasing the entire time, reaches the top and gets 0, and then it becomes negative after that because it's falling and getting faster. So those are some really important concepts of projectile motion. We're going to talk about applications and calculations and things like that in class. We're going to do a bunch of different labs and activities along with this. But hopefully this gives you some idea of what's happening in the horizontal and vertical direction. How are they different from each other? How are they independent of each other? And we can build on our conceptual understanding from there.